Hello and welcome guys, my name is Steve and welcome back to my channel. Welcome back to the Concurrency in Go course, and this is the second part of this topic, which is atomics. First of all, if you have not watched the first part of this topic, make sure to watch this video right here. And also, before we dive into any kind of coding, presentations and all that stuff, make sure to check out the GitHub repo where you will find a downloadable zip so that you don't have to write code by hand, so that you can follow along as we progress in this video. And now let's not waste a lot of time and let's dive into this part. So now that you know what are atomics, how to use atomics, and pretty much everything basic about atomics, let's dive into a couple of behind the scenes regarding atomics and how they work. Specifically, I want to talk about the compilation phase and what exactly happens when you compile your code which also uses atomics and things which work with atomics or like atomics. So first of all, you have your Go application, which has a bunch of Go files, which has Go code. Then you have the Go compiler. The Go compiler will try and parse these files. Before it even compiles your code, it will have a look at something called Go OS and Go Arch. These are variables which you can set yourself or Go will set for you depending on your operating system and your architecture. So once Go has successfully compiled your code, it will basically generate something which is called Go ASM. Now Go ASM or Go assembly is something which looks and feels like assembly, however it's not real assembly, it's pseudo instructions. They're not real instructions which will run eventually on your operating system and your specific architecture. Because of that, the Go ASM has to be interpreted by something which is in between, something which is internal to Go. That something is the obj library. The obj library, given a specific input, a specific struct which Go understands, which that library understands, will try and throw out and spit real instructions which work for your specific operating system, for your specific architecture. So this is the table or the list of architecture which Go supports. As you can see, it's plenty of them, it's a lot of them. So basically the obj library will try and map them to real instructions or instructions that will run on your specific machine. After the obj library has successfully done its job, it will generate an object file. All that is left to do is for the linker to take that object file and generate a binary out of it. So this is the purpose of the linker, to take in a bunch of object files, kind of compose them, merge them together, and generate the binary out of that. That binary is nothing else but zeros and ones, which our CPU understands, and thus our CPU will execute that in the end. This is how the process looks from the compilation point of view, and the question still remains the same: where do atomics fit in? To answer that question, let's have a look at another diagram of how exactly the go build command works. Let's say you run go build on your machine. What actually happens is a lot of processes are involved in this specific step. Let's say you have a couple of files on your machine. You have main.go, you have add32_amd64.s, and you have the same one for add64. Now what's all that fuss around these .s files? If you ever had a look inside the standard library, you probably saw a lot of these .s files and all these weird names. What exactly are these files? Well, to give you a very short answer, these files are nothing else but Go ASM, Go assembly, or Go pseudo assembly instructions. So from this process, when you run go build, two things will happen. First of all, it will happen the compilation phase, meaning it will try and compile all your Go source code. In the compilation phase, if Go detects any kind of functions which has missing bodies, it will try and look for external implementation, meaning it will try and look for Go ASM files. So at this point, if Go has detected any kind of Go ASM files, it will try and apply the Go ASM tool. What that means, it will try and generate object files from these ASM or assembly, pseudo assembly instructions. And again, all that is really left to do is to use the linker, and the linker will take all these object files and generate a binary for you so that you can execute it on your machine. Now, with all this being said, with all this mouthful of explanations, let's dive into a couple of examples. Let's explore the standard library a little bit. Let's try and replicate the math package and use a couple of those functions, use a couple of those Go ASM files. If you open up a browser and head over to golang.org/ref/spec, you will find some very interesting details. And I want you to look for something like function declarations. And what I want you to focus at is this specific statement right here. A function declaration may omit the body. Such declaration provides the signature for a function implemented outside Go, such as an assembly routine. So what this basically means is it can actually have its functionality declared outside Go code in assembly code. Let's go ahead and create an example ourselves and actually play with this and see if omitting the body of a function will actually give us something in return. So inside the same directory, I'm going to create a new one called, for example, example, no function body. So let's say something like no func body. And let's create a simple example. As usual, a file called main, package main, and of course, func main. So let's say something like, for example, func, and let's say, I don't know, let's say dummy func, let's say accept an integer, and let's say it returns also an integer. This is pretty much it. No curly braces as we usually do. Now, when you try to run this example, we are obviously going to get an error which says missing function body. And even if you try and call this function, it's still going to give you the exact same error. So let's say we call dummy func, and let's say we call it with the argument of 10. If you try and run this example again, it's still going to say missing function body. And let's go ahead and fix that, solve this by using Go ASM. So to give you a good idea of what is Go ASM, we're going to try to replicate the math package inside the standard library. Specifically, we'll want to replicate the square root function and of course the floor function. So let's create a new directory and let's call this one ASM. And of course, as usual, let's create a main file. So let's say main, package main, and of course, func main. So first of all, let's go ahead and declare the square root function, which is the exact same declaration as it is in the math package. So let's say something like func, let's say sqrt, and it's going to accept a float 64 and as well return back a float 64. If you want to convince yourself, let's say something like math.square root, and as you can see, math.square root returns back a float 64 and receives a float 64. So we are good to go. And let's also declare another function without the body, and this one will be floor. We have to provide the implementation, which as that article said, it has to be outside Go. Now, outside Go really means it has to be inside Go ASM, or in other words, Go assembly. And Go ASM or Go assembly files usually have the extension .s. And if you provide in underscore and a specific architecture in the name of the file, when you're going to use the Go build tool, it will actually pick that up and use that for your specific architecture. So all that mouthful of words being said, let's go ahead and create these Go ASM files. So let's say file, and this one will be sqrt underscore amd64.s, and I'm going to copy and paste this one and create the same file, floor, for example. Now, first of all, let's go ahead and copy the implementation for the square root function, and the easiest way to do so is by simply navigating the standard library. Let's simply say something like math.square root, and it's very easy to do so on pretty much any IDE or text editor. All you have to do is hit Command or Control and click on this function, and as you can see, it will redirect you inside the math package, inside the standard library. In fact, inside the IDE, I have this little thing which will actually redirect me straight into the file system where this standard library is found. And as you can see, we have this sqrt.go file, and next to it, we have sqrt underscore amd64, which is the exact architecture that I'm running on at the moment. Also, if you have a look at this specific declaration inside the math package, and this is again a function which pretty much looks the exact same way like our function inside main.go. And yeah, it's a function which doesn't have a body, which means it will expect to be picked up from a specific architecture, and our architecture is AMD64. So if you want to query your architecture which is set inside the Go arch variable, all you have to do is run something like go env, and let's say you want to grep or look for something like, let's say, go arch, and it will give us back AMD64. So I know I am on AMD64, and everything that is AMD64 will get picked up by the Go build tool, compiler, and so on and so forth. This is the variable which will get passed along every tool which Go uses behind the scenes. So we know that this function doesn't have a body, and we also know that our architecture, my architecture, is AMD64, and inside this file you can find the implementation, you can find the Go ASM code. So let's go ahead and copy this one, paste it inside sqrt underscore amd64.s. First of all, this no split thing, you want to delete this because this is important from a specific library which Go uses internally. So I will simply go ahead and remove this one, and let's also add in a new line at the end. So if we go back inside our main function, now we can make use of this sqrt function. So let's simply say something like funct println, and let's say sqrt the result, let's say sqrt, and let's provide in the value 25, for example. Normally we should get back 5 because this is what would get returned from the math package. And for that, let's open up a new terminal. Let's go ahead and cd into ASM, and let's go ahead and generate a binary first of all. So I'm going to say go build -o. Let's say we want to call this one exec. And as you can see, this one is also asking for modules and all that stuff. And this is why I will simply put this inside or on top of this root directory, perhaps change this to concurrency. And now let's get back to our example. And if you open up the exact same terminal and you run this again, as you can see, see we have successfully generated an executable. And if you try and run this executable, it in fact will execute that. When you're using a function without a body, you're expecting somebody else, in our case, Go ASM, will have to implement that for us. It's pretty much like in C. If you have studied C in university, it's pretty much the same exact idea. You provide in a header, you expect somebody else to implement this for you. So now all that is left to do is actually go ahead and fill out the external implementation for this floor function. So again, it's very simple to do so. Math dot, let's say floor, and let's simply, again, command or control and click on this. As you can see, it's yet again a function without a body, which means it must have some kind of external implementation. If I hit click on this one, as you can see, it has this floor.go file, and next to it, it has the ASM files. It has floor 386 and floor AMD64. I want to open up this floor AMD64 because this is the implementation for the specific architecture that I'm running on. And copy this and paste this, of course, inside our file. And yet again, we want to get rid of this one. We also want to make sure we import this big constant. And yeah, let's open up this file yet again. And as you can see, they have defined a big constant. So I'm just simply going to copy that and make sure we paste this somewhere in here so that we don't get an error. New line at the end of this file. And inside our main function, all that we have to do is remove this call right here. And let's duplicate this one. And let's say floor result, for example, and let's call floor and pass in something like 2.33. First of all, let's go ahead and regenerate the binary by using the go build. And now let's go ahead and run this binary. And as you can see, it pretty much works. A square root result is 5 and the floor result is 2, which is pretty much the exact same implementation as in the math package. Now let's go ahead and create a custom print function, which will actually reference code from Go ASM, and the Go ASM will reference Go code. That's pretty interesting. And let's see if that's going to work, if that kind of experiment will work. So let's go ahead and say something like func ASM print result, for example, and let's say we will receive a float 64 and another float 64. This function will be referenced by the Go ASM. So let's create the actual function which will print things. So let's say func print result, and now let's go ahead and cut these two statements and paste them right here inside this print result function. And instead of executing these functions directly inside the print result, we want to receive them as arguments. So this function right here will pass these two arguments to this print result function externally from the outside world. First of all, we want to receive something called square root result. So let's say sqrt res, and we want floor result, so floor res, and they will both be float 64. And now we want to print this result instead of calling these functions directly. So let's print something like sqrt res, let's say floor res, and inside our main function, let's call, instead of print result, let's call ASM print result, which will be declared externally. So let's print something like ASM print result, and the first one has to be sqrt result. So let's say something like sqrt, and let's provide in 25 like before. And the second one has to be the floor result. So let's provide in floor and 2.33. And now here's the interesting part. We have to declare this ASM print result function outside because that's what we're saying here. We don't have a body, meaning somebody else outside the Go ASM file has that body for us. And that body will call this print result function. So let's go ahead and quickly do that. You will see it's actually quite easy to do so. So as a reference, I'm simply going to copy this sqrt underscore AMD64 file, and I'm gonna paste this right here and rename this to something like print AMD64. So let's rename this to print AMD64. So first of all, this one has to be called ASM print result. So let's name this one ASM print result, and then let's delete all this stuff. And now let's go ahead and copy this weird dot, and let's actually make sure we call a function from our Go code. And that is very simple to do. All we have to do is say print result, which is that function which we declared inside our main, and let's call this one with SB. This is pretty much it, how you call a function or how you call a Go function from Go ASM. Let's go ahead and compile, or I should say build our code yet again and see if that will actually work. So again, if you open up your terminal and you regenerate the binary and you run this binary, you should see pretty much the exact same result. However, this time around, we are not printing anything inside our main function. Inside our main function, we are calling this ASM print result function, which is declared externally, which in turn calls this print result function, which we have declared inside our Go code. So this is how you reference Go ASM code from Go code and how you reference Go code from Go ASM code. This is a powerful thing, so you have to to be careful about it. You have to use it with care. Again, Go ASM is nothing else but pseudo instructions which map to real instructions in the end once this compilation phase is done. And also don't forget about the Go arch variable. You can set the Go arch variable yourself, or Go will set this for you. In my case, it's going to be AMD 64, which is 64-bit. So in the end, you will get an object file which has real instructions, real AMD 64 instructions in my case. And that in the end will get linked by the Go linker. And in the end, we will have a binary zeros and ones, which our CPU understands, which our CPU can finally execute. So let's go ahead and run a couple of commands based on this ASM example and check out a couple of things which yet again happen behind the scenes. Yet again, cd into ASM. So to compile your program, it's very simple. All you really have to do is run go tool, and there is a tool called compile. Compile will also accept an option called s, which will generate verbose output. So let's say -s, and let's provide in main.go. So after the go tool has finished compiling your program, it will actually generate an object out of it. If you want to see it, you can simply do an ls, and you will see there is a file called main.o, which is an object file, which will then be used by the linker to generate a binary out of this. And you also have this verbose output. These are basically instructions, or I should say pseudo instructions, used by the object library and used internally by the Go tools in order to generate actual instructions which will run on your specific architecture, in my case AMD 64. If you want to save all those pseudo instructions or all that Go ASM code in a specific files, you could rerun this command and redirect this output to something like main.s. And as you can see, we have a main.s file right now. And if you cut, for example, main.s, as you can see, we have the exact same pseudo instructions. We have Go ASM code, which will then be used by internal tools in order to generate actual instructions and generate an object out of this in order to be linked and thus create a binary out of it. As I said before, what the Go build tool will try and do is also try and parse these .s files, which are Go ASM instructions. It will try and parse them and try and generate an object file out of them. To generate an object file out of the square root AMD 64 Go ASM code, all we really have to do is pretty much run the same go tool command. So let's say go tool, and this time around we have another tool called ASM square root AMD 64. And once you do that, as you can see, you have now an object called square root AMD 64.o, which is again an object which can be linked. Speaking of the linker or the tool which actually takes in your object file and generates a binary out of it, let's create a dummy main function which will print out something. So inside the ASM directory, I'm going to create a new one called link, for example, and inside this directory I'm going to create a main file. Let's say something like main, and as usual package main, and let's say func main. Let's say something like func print line, let's say hello world linking. And once I have all this, let's go ahead and generate an object file out of this. So again, I'm going to open up my terminal and I'm going to cd into ASM into link. And once we are here, we want to generate an object file out of this, and it's very easy to do so. All we have to do is simply call the compile tool. So let's say go tool, and let's provide in compile, and let's say something like main.go. It will generate an object file, as you can see. And now let's go ahead and use the link tool or the linker, which will go ahead and link that object file and generate the binary for us. So let's say something like go tool, let's say link, and provide in the object file. So let's say main.o, and as you can see, it has successfully generated something like a.out. We could have said something like this, and let's say something like -o. Let's call this one exec. And when you check this out, we have a binary called exec as well. So if you run an exec, as you can see, it will pretty much print the exact same statement. Now there is one more interesting tool called objdump, and you can use that tool in order to inspect a binary for what kind of instructions actually got dumped into that binary. So let's go ahead and run something like go tool, and let's say something like objdump, and now we have to provide in the -s option, and let's say something like main.main, because that's the function we want to inspect. And let's also provide in the name of our executable. So let's say exec, and when you run this one, it will actually show you the actual instructions which got dumped into this file. And as you can see, these are the instructions which we are using in this specific binary. So this is a very neat feature, because this way you can check out what kind of instructions exactly are happening inside your binary. And now that you know a little bit Go ASM, how to work with Go ASM files, how all that works behind the scenes, let's try and implement atomics from scratch. We'll implement a very small fractions of atomics. This is why let's not waste a lot of time, and let's dive into this example. New directory, and let's call this one atomic implementation, and let's create a main file right here. So let's say main, and as usual, usual package main, and of course func main. Our wait group is going to be a sync.wait group, and after that, of course, we want to wait. So let's say wait group.wait, and let's say after we wait, we print something like func print line, and let's say count, the value of the count, which we'll have to create a new variable declaration. So let's say var count is going to be an int 64. First of all, we want to add 100 because we want to listen for 100 go routines. So let's say wait group dot add, let's say for example 100, and now let's fill out that for loop. For I is going to be equal to 0, I is going to be less than 100, and I plus plus. Let's say go func. And before we proceed with anything, as usual, defer wait group dot done. And now we want to call this function called store int64. So let's say func store int64. It has to receive some kind of address. So let's say address is going to be a pointer to int64, and then it has to receive some kind of value. So let's say value will be the actual int64 which we want to store. So let's make sure to call store int64 and provide in the address which is count, and also provide in the delta or the value which we want to store. So let's say int64, and we want to provide in I plus 1, and of course we want to pass this I as an argument. So let's say I is going to be an int and provide in I like that. So this is pretty much it when it comes to the Go code. Now all we have to do is provide an implementation for this store int64 function. To do that, the simplest way is yet again to explore the standard library and steal it from there. It has to be in some kind of Go ASM file. So yet again, the simplest way to do it is simply by exploring the standard library. Let me just simply say atomic.store int64, and as usual, hit command or control and click on this one, and it should redirect you to something called doc.go. And as well, I will click this icon right here, and as you can see, we have this doc.go right here, and we also have something called asm.s. What I want you to do is open up this asm.s, and as you can see, it has a function declaration which is called store int64, which is exactly what gets called in here, and it has an instruction called jump, which was basically going to jump to a different piece of Go code. It's going to jump to runtime, internal, atomic, and the function name is store64. So let's actually close this one and let's jump into runtime. So let's look for runtime, and runtime will have something called internal, and inside internal we have atomic, and atomic has something called atomic AMD64. This is the one which we want to open up because in my case is AMD64. Open this one up and let's look for something called store64. We have the function store64, and yet again this function is a function which doesn't have a body. So again, if you have a look at all these ASM files, we want to open up for this specific architecture ASM_AMD64.s. So if you look for store64, as you can see, this is the exact same path which is provided. So this is pretty much the implementation that we are looking for. This is why I'm going to copy this one up, and I'm going to try to paste this in a file which we will have to create. Let me go ahead and create a file called atomic AMD64. So let's say new file, let's call this one atomic_AMD64.s, and let me paste this one in here, add a new line, and of course this is going to be named a little bit different. So let me remove all this, keep the dot, this is very important, and let me call this one store int64, and of course remove this no split because we don't use this, and I believe this should be it. Let's go ahead and try and test this using the raise flag as well. So again, open up your terminal and let's cd into atomic implementation. So if you go ahead and run the exact same build command, but this time around we're going to provide the raise flag. As you can see, it generated the binary, and now when you execute the binary, it will execute that binary using the raise flag. So when you execute the binary, as you can see, we have a working implementation of atomics. Now it's not the entire implementation of atomics, but it proves that this is exactly the way and the principle atomics work. They work on the CPU level, and they work by having these functions without a body and having external routines declared inside external files, which are nothing else but Go ASM. So before we wrap this video up, I just wanted to walk a little bit of an extra mile and show you the source code of the Go build tool. And we want to go into a very specific location in order to find out the build command or the build tool. And you want to look for some something called CMD. You want to go inside CMD. After that, you want to go inside something called ASM, and then inside internal, and then inside Arch. You want to go inside Arch, and here you will find a file arch.go. Open up arch.go, and when you open up arch.go, somewhere around here you should have a function called set. So inside this function called set, as you can see, it accepts a variable called goarch. So basically goarch by default will be your current machine's architecture, but you can really set this up to your liking. And as you can see, these are all the architecture which Go supports. There are plenty of architectures, including our architecture, which was AMD 64. And as you can see, this AMD 64 calls something called Arch x86, which is part of the same family. And this one pretty much sets all the instructions. And this is exactly the place where all this mapping of pseudo instructions to real architecture instructions happens. And lastly, you can also have a look at the obj library. And inside the CMD directory, you have something called internal. So let's cd into internal. And inside internal, you have something called obj. And here you have x86. And inside x86, you have something like a names. So let's say a names.go. And here are all the freaking instructions which are available for x86. As you can see, you have plenty of them. I hope this extra mile was interesting and intriguing for a lot of you. This is why make sure to check all of this out by yourself, because there's too much stuff to check out. And yeah, hope you guys like it. Hope you guys enjoyed all this extra mile. Atomics are nice. They're amazing. They're blazing fast, but you can't really use them for everything. This is why in the next lectures, we will explore more types when it comes to the sync package and when it comes to concurrency in general. All right, guys, this is pretty much it on this topic. This is pretty much it on the part 2. I hope you guys enjoyed atomics. Hope you guys now know more about atomics and when to use them, how to use them, and all that stuff. Like in the previous videos, I'm going to provide you with a zip archive so that you can download without worrying about typing everything that we wrote in this specific video and the previous one. And as usual, if you enjoyed this video, if you found any useful information in this video, make sure to like this video and share this video so that others may know about it. And like always, if you're not part of this community, make sure to hit that subscribe button over there and become part of this community and not miss a single video. And speaking of community, make sure to head over to the description of this video where you will find a link to the Discord server so that you can join the family. And lastly, guys, I've been doing YouTube for 4 months already, so if you feel like contributing, feel free to do so and head over to that Patreon page. Or if you feel more comfortable with a one-time donation, PayPal is as well an option. This sums up our part 2. This sums up our topic regarding atomics, and I'll see you guys in the next video. Peace.